Good. Okay, so that's going to continue with Corsets.
Thank you. So yesterday we started to talk about, for example, mean queries, and we constructed some courses, but it was very specific to a specific problem. For example, in the mean queries, we assume that we have n point. The query was another point or a center. We want to compute the sum of square distances for this point. And we showed that using simple algebra, you can just compute the sum of square distances, but it was a bit strange in the sense that it was not exactly just subset of the input. The error was 0, and it was very specific for this problem. And the same with the one center, the k center problem that I showed yesterday. Today I want to show you a technique that how to make courses for your problem, or you classify your machine learning model, and what are the main problems that you need to challenge. It's kind of a reduction for the original Corsets problem to some other optimization problems that you need to solve that might be much easier. So, for example, using this framework, we were able to solve the k-median queries or the k-mean queries, where the input is n points in RD. The query or the candidate set of models is a set of k points. And you want to take the sum of distances for every point to its nearest center. And k-mean is the sum of square distances. And of course, once we have such a Corset that approximates every q, we can also solve the optimization problem using some constraints in the big data model, as we talked about in the previous lectures. So again, we will now try to find a weighted subset, but in a more general way. But we won't use the grid. We actually will still have some kind of weighted points, but and the property will be the same for every set of k center. The sum of square distances or the sum of distances for the original point and the Corset, which is the red points, will be approximated the same. But you won't use the cells in the grid that you used yesterday because there's exponential in the dimension. They're too expensive. We use random sampling, a non-uniform random sampling more precisely. So to give motivation for this framework, other problems, so sometimes because the Corsets derive from computational geometry, people think that it's mainly good only for problems in computational geometry, but actually most of the machine learning problems and new classifiers are essentially problems in computational geometry in the sense that you can present the classifier as a simple geometry shape. For example, consider the case of, for example, the Google PageRank, or in general, the problem of finding the largest eigenvector of a stochastic matrix. We want to find x such that ax equal x. We can just rephrase the problem as compute x such that this equals 0. And by just playing with the notation, we can define a matrix P, and we have optimization problem when the optimum is 0, because we know that there is some x such that ax equal x. By putting this P here, we get that this equals 0. So we actually want to solve this optimization problem. And we can solve in PageRank or Heat's algorithm, for example, for the web search, how we do using different P, we essentially need to solve the same problem, which seems to be very problem in algebra and nothing to do with computational geometry. But actually, there is a simple interpretation for this model. So suppose that you want to find the minimum, the x of norm 1 that minimizes the sum of square distances. And 1 plus epsilon approximation means that it's not optimal, but it's 1 plus epsilon multiplied by the optimal. So the cost is almost the same. And to see the connection to computational geometry, and in general, like in superposed vector machine, there are a lot of other classifiers, including neural networks, that people usually don't think in terms of computational geometry. And trying to give you simple examples why, especially when you deal with matrices, essentially everything is about geometry. Because in this case, for example, norm px squared, what is it actually? So it's sum of squared inner product between every row in P and x. So you take the first row of P multiplied by x, take the squared, and continue to the next row, and so on. So if you think about the hyperplane, or in the two-dimensional space it's just a line, thank you, and you think of x as the orthogonal unit vector to this hyperplane, then the inner product of a row P in the matrix P and X is just the distance to H, to the hyperplane. So norm Px squared is just the sum of square distances between every point to the hyperplane that is orthogonal to the vector Ex. So in other words, we can say that we are looking for the hyperplane that minimizes the sum of distances, sum square distances to the original points, which is exactly the same problem. And more generally, sometimes you want low-dimensional subspace, like in the text mining LSA topic models. So in general, we might want to look for some j-dimensional subspace or affine j-dimensional subspace or an affine mean that not necessarily pass through the origin. So that the sum of square distance for the original point to this subspace will be minimized in some sense. So we want a good low-dimensional reduction for the input points. In the concept of course, if you want corsets for this problem, again, the input is points, the query is just j subspace, and you want to approximate the sum of square distances to every such j subspaces. So again, input, query, and cost function. The corset is almost the same. Now we just select weighted points. So again, the output, the corset is always points, not lines, not subspaces. But the claim is now when you give me a query subspace, the sum of square distance for the original point to this subspace will be approximated by the corset points to this subspace. So if you do dimensional reduction and you want to find the line or the subspace that minimize the sum of square distances, you can also use the corset. In general, we can also use, for example, projective clustering. For example, instead of k-means or j-subsets, we want to combine them. So we want several SVD to cluster the point to several dimensional spaces. For example, in the case of lines, we want to approximate the points by k lines, such that every point go to the nearest line, which is a generalization of k-means or k-median for the case of lines. And in general, we can talk about k j-dimensional subspaces. Now, all this problem can be solved using corsets. And again, this is the result for the last few years. And I'll try to give you the general framework now how we can construct such corsets. And I will use the same definition from yesterday, which is very, very general. And we use this definition to show that if you have corsets with this property, then you can handle big data, streaming data, and parallel computation. So I use the same cost function that we were able to plug into the tree from yesterday. Just to remind you, we talk about a general set. Usually this is the points or the input that you want to approximate or the documents or whatever. Q is infinite set of queries usually. Cost is what you want to approximate over all the points. And the definition of a corset is that if I give you a subset from the general set and some error parameter epsilon, you want to find usually a small subset such that for every query, the cost from P to the query and the cost from the corset C to the query is approximately the same. So it's not too large and not too small compared to the value that you want to compute. Now, I don't have a general framework for all the problems in the world, but we have a general framework for quite general case. And the case is where the cost function is a sum of some other function. I called it distance, but it's not necessarily a distance function, just for the intuition. Where this is a function for every point, for every query, give me a number. Intuitively, the distance from the point to the query. And what you want to approximate is the sum. So if you want, for example, for k-means, this will be the square distance between a point and the nearest point in the k-center. So you can put this square distance to the 0, whatever, or strange other distance function that you need, like in mixture of Gaussians or whatever strange function or distance between distributions. And if you have this property of the cost that is sum over something, then we can prove that if you just take a non-uniform sample according to this distribution, so the probability to choose a point P is just the sensitivity, which means how important this point is. So over all the queries, what is the main contribution? What is the maximum contribution of this query? So what is the worst case? What is the case that this point P contributes at most to the general cost. So this means the sensitivity of P. And the theorem that we'll prove now, and we see how to use it for some example, is that if you have this distribution, then only need to take this number of points according to this distribution, and you'll have a corset. So what is written here, this is a sum of all the sensitivities. So again, we hope that this will be less than n, less than the original number of points. And this is 1, but we want to find good bounds, so this sum will be at most, say, log n, much smaller than n. Epsilon is the error, the approximation error. We defined it in the previous slide. Dimension of Q we will define now. And intuitively, it's related to VC dimension of the query space. Or practically, it's how many parameters you need to define a query. So for example, if it's just a ball or a point, you need the coordinate to define this point. If you have polynomial, it's usually the degree of the polynomial. So the complexity of the structure of the queries, I'll define it a bit more formal now. And just to give you a quick example of how we actually use it. So for example, for the k-means, we're able to prove that the sensitivity of the point, of each point, is its distance to the optimal solution divided by the sum of distance to the optimal solution plus 1 over np. So Q star is the optimal solution, k means, if we talk about square distances, so k median if we talk about sum of distances, and np is the number of points in your cluster. So as I mentioned yesterday, if you're in a very small cluster, you'll be selected with high probability. But even if you're a large cluster, but in a very far from the center, you'll also be chosen with high probability. And the VC dimension is known to be KD. So we have KD over epsilon squared multiplied by the sum of sensitivities, which is K. And we get a corset of this size. Now, over the year, we combine corsets with other corsets. For example, yesterday, we showed a technique that we took a points P, we project them on endpoint P prime, and then we're able to have a corset for P prime. To get rid of this D, for example, if you have endpoints in n-dimensional space, we show, for example, in the last soda paper that you can just compute PCA and take the k over epsilon singular vectors, the k over epsilon leftmost singular vectors, and project the points on this k over epsilon dimensional subspace. So you still have endpoints, but like yesterday a bit, now they're in a low-dimensional space. And now we apply this technique, this sampling, and this D now replaced by k over epsilon because the points are now lying in the k over epsilon dimensional space. So we combine the PCA with the non-uniform random sampling technique to have smaller corset that of size. Note that this is independent, totally independent of the original data. Independent of n, the number of points, independent of d, the dimensionality. It only depends on how many clusters you want to approximate and what is epsilon, what is the error. Questions till now? Good. So let's go to business. So I will first show you how to prove the claim, how in general, why in general we can compute corset using random sampling, and what exactly we need to bound. And then I try to show some examples of how we compute this reduction. So we reduce the problem to a very simple optimization problem. And then I will show you how to solve this problem for the k-mean, for the SVD, and hopefully it will help you to solve the problem for your the classifier that you are interested in or researching. So let's start. So it might be, again, I'll start with this. So even if you see a lot of equation, I'm not going to cite any complicated theorem in math, in quantum physics, or computational geometry. All I do will just multiplication and move parameters from side to side. Sometimes it will be long, it looks maybe a bit complicated, but there's nothing there. It's not even linear algebra, just high school algebra. But it still took a lot of years for me and a lot of other people to come up with these ideas. But when you see them, think that they're really, really simple, very easy to implement, and I hope that you can use them. So in general, I need to define the PW. So P is a set of points from X, and W is just a weight function. So remember, even if your original data is just a set of points, without weights or vectors or chairs or whatever, if you remember yesterday in the tree, we had to compute corset for the corset. So even if the original data is not non-weighted, the corset is usually weighted. And then during the tree, we want to compute corsets for corsets. So usually the input will be weighted. Because if the original data is not weighted, the corset is weighted. And to compute corset for corset, we need to assume that we have some distribution of each point. So we assume that we have a weight function. So P is just the subset from our ground set. Usually points in this talk, but maybe in your case it tensors or metrics or documents or whatever. And W is just a weight function. Without loss of generality, we can assume that actually the sum of weights is 1. Otherwise, we can just scale everything and divide by the sum of weights. So weight is just importance of distribution over the data. How important is this each point when you compute the cost? And now we want to define the query space. Definition, query space. So we assume that we have F, which is a bit like this that I showed in the last slide, but slightly different. So for every point and for every query, you have a number. How this point contribute to the query. And what we wish is usually to compute the cost, which is the weighted sum of distances. So we have points, we have weight function, we have the query, and we define it as the average cost. So go over all the points. We take the importance of the points as the first parameter. And then we multiply this by the contribution of F for the point P to the query Q, and we sum. So this is kind of a weighted average on the cost for every Q that you give me. So this I will just call the tuple P, W, Q, F is called a query space. So when you begin to try to find a corset for your problem, your first thing you need to define this. These 4 parameters. What is the input? Distribution is the input, usually just uniform 1 over n for each point. What is the set of query? Sorry, this is large Q. And what exactly you want to compute? Distance, square distances, sum of distance to mixture of Gaussian, suppose a vector machine, whatever you want. And these 4 variables we'll call the query space. And how it is related to our problem, what we want to approximate is the cost. So the first thing I need is to get rid of the multiplication factor 1 plus epsilon and move to additive error epsilon, which is more popular and more useful in statistics and related to the tools that we use. So suppose that that we have these properties. So we have 2, this is the original query space. And suppose that we found the new query space, which will be the corset. So it's work on the same function and the same queries, but the weights are different. They will be sparse. Most of the points will get 0 weight. And this will be the subset of P that we choose. So this will be the corset. And suppose that for this space, for every query, we have this additive error. We know that this minus the average cost of the corset is less than epsilon. How does it help? What we want yesterday is to talk about 1 plus epsilon multiplicative factor. And the trick is just to observe that by letting FPQ dist PQ divided by cost PQ. So I just define the function instead of sum of distances, whatever defined distances, instead of sum of distances, I will define f to be distances divided by the total cost, which is the same as this PQ, the contribution of this point, divided by sum, the weight of the point. So this is just the total cost. So if I define this function based on distance cost from the previous slide, if I can prove you that I have this property, then we have Corsets as we defined before. Why? Because I think we can put it like this. Because we have, this is what we really want. We want cost PQ minus the cost of the coset Q. We want this, the error between this, the cost of for the points and the cost will be epsilon this, which means 1 plus epsilon factor approximation. This was also the equation that we wrote on the board yesterday. So 1 plus epsilon approximation means that the difference between these two is epsilon multiplied by the original value. This is 1 plus epsilon approximation. So I want to claim that if you have this, then you have this. Why? Because the cost is just this, right? Where the sum is over the points in the original set. And on the other side, we have this set, the point on the corset, with their weight. But now, what is the connection between this and f? So f is this divided by cost PQ, which is independent of the specific point P. So what we do is just replace this by fp multiplied by cost. This also fp multiplied by cost. So this is just cost PQ. I take it out, multiply by the fp, wp fpq minus sum up fpq. Right? I just replace this by f and take the cost out. But this is exactly, by the definition, cost PQ the average of PW to Q minus the average on the corset using the weight Q, using the weight U. So this was the definition of the average F here. But if I can prove that this is epsilon, we get this is epsilon cost PQ. So all these will just substitute playing with the notation. So instead of distance cost, we just have one function. And now we want additive error. So we want that this difference will be less than epsilon, not cost. So this is the first step of the reduction. Let's work now. From now on, let's work with F and prove that you have epsilon additive error. And I already told you how to move from constant this to this F. So during the years, a lot of papers will come out with different construction, deterministic construction, random construction. And we show that actually what we really want is, Corset is kind of a just generalization of the classic epsilon sample from Vapnik for 71. You probably learned about VC dimension, pack learning. So I want to show that it's simple reduction. So if you want to know how to do VC dimension and asking cost sensitivity for the points, then you have a Corset. And if in pack learning we just talk about uniform random sampling, I want to show you how we can change this to non-uniform random sampling and get a Corset. And for this, we just use the definition of epsilon approximation, or epsilon sample. There are a lot of names very related to epsilon net from Vapnik. So a weighted set, this is the definition. A weighted set Cu is an epsilon approximation if for every Q in Q we have this. The weighted average, the sum of distances to Q minus the sum of distances to, for the corset, we wish it will be epsilon, and since usually we have millions of techniques how to compute epsilon approximation, including uniform random sampling, we can go home, but we don't. We have this annoying factor here. So the intuition behind this is, for example, if you think about Chernoff inequality. So suppose that you have millions of numbers between 0 and 1. And you want to know what is the average number. So we have a technique from statistics, like Chernoff-Hoeffling inequality, that says if you just sample something like 1 over epsilon squared points, with good probability, with constant probability, with small constant probability, the average of the sample would be a good approximation for the average of the original point. So that's exactly what we do in before elections, right? We check a subset of people, ask them, would you choose for 0 or 1? And then we decide who will win the elections, right? If you want to know how good was the exam, you just ask 10 friends. If all of them failed, you probably also failed, if you just a random sample from the test. But in general, if you want to know the average, we can just take random sample. The problem is that this work if the number is 0 or 1. But if a single person had a million of votes and you missed it, then it's a problem. So we assume here that everyone has the same sensitivity in some sense, all the people importance in the same way. But in practice, for example, if the number can be between 0 and million, so this person is 1, can contribute 0 or 1, but the other can contribute 0 and million, it might be that everything is concentrated in one person, and the error will be large. The error will be epsilon multiplied by a maximum value. So the problem is that when we talk about distances for k-centers, the distance of each point can be very large. We don't want to assume that all the points are in the unit cube or something like this, and all the queries are in unit cube. So in general, these values can be very large, and that's why we have this error. So just using, for example, random sampling can give you epsilon approximation, but the error will be too large. So the next tool to get rid of this one, and again, I still don't tell you how to compute epsilon approximation. There are a lot of ways, deterministic, randomized, millions of papers. The classic way is just uniform random sample, but for now, just assume that you know how to compute this. How can you get rid of this max and just get epsilon here? So this is where the sensitivity comes from. So it was a paper by, there was a paper by me, Christian Zoller, and Mendoza Morteza that show how to do this specifically for k-means. Definition for sensitivity for k-mean was later by Schulman and Langberg. And then in Stock 2011, we essentially presented this work. It was with Langberg that we show in general sensitivity for all the problems in the world, how you can reduce everything to epsilon approximation if you know how to bound the sensitivity. And it's amazingly simple. And again, you're just playing like before with the equation and you get this result. So suppose that SP, this will be the sensitivity, is just the maximum contribution over all the query for a specific point. So I remind you that FPQ was the contribution of point divided by the total cost. So this, consistent with the previous slide, so it's just the maximum contribution compared to all the other points of all the queries. So suppose we have this number, and we just scale the data. So if the point is very important, we'll give it a high weight, and we sample it with high. So epsilon approximation talk about uniform random sample. So we just duplicate the point a lot of time, and then if you do uniform random sample, we will choose it with high probability. So this is intuition that we could take points that are very important, just duplicate the minimum of time. So then we can say just take uniform random sample again from this set. So this is SP. So the new weight for the set. So we have a weight function again. We defined it to be the original weight, or I forget, and T is the sum, C is the sum of all the sensitivity of all the points multiplied by the weights. So T is the sum of weighted sum of this SP. Again, it's both of them independent of a specific query. You can compute it before you get any query for the cost of construction, these two numbers, S and T, S for every point and T as the sum. And we define this to be SP over T. So what is your sensitivity? Compared to the overall sensitivity, the total sensitivity, multiplied by the original weight. So if you was very important in the beginning, we still want to give you the credit. So this is the new weight function on the points. But again, we want to change the weight and probability so that for every query, the cost will still be the same. So we need to change also the function. So we define a new function. So again, this is a function that we can put in a query space. And we defined it to be like this. It's just the original function, the original function divided by SP, this value. So if I give you a query, instead of computing the original cost of your point to the query, you divide it by SP, which is the importance of this point. And note that the weight, here SP is above, here SP in below. So when you compute the weighted F, they will cancel each other. So next thing is suppose that CU is an epsilon over T approximation for the new set. So it's the same set of points, but a new weight function, the same set of query, and a new cost function for each query. What we can say about C? And the claim is that we have the property that we want. For every Q, the average weight to a query for the original point minus T multiply by the average weight of the corset is epsilon without the max here. So actually this is a corollary. There's not too much to prove here. Just plug in the parameters and let's do it together. So suppose that we fix some query, and by the way that you choose the weight in the new F prime, we get that WP FPQ, which was the original cost for a point, is exactly the same as T, which is kind of a constant, multiplied by W prime P F prime PQ. So we just play with the W and F prime, so the sum is essentially the same. W is smaller, F is larger, but everything cancels out. So the cost is almost the same up to some factor T that we can pay in the corset. So we have that this cost equal to the cost of F prime. Okay, so we can forget about F, and now I try to bound this one. But what is this? So again, from this we have that what we actually want to have, which is this value, is exactly the same as the error from F prime. So instead of bound this, we just need to bound this. But we already know that CU is an epsilon approximation for this set, for PW prime Q. So what is this? So we have that T, blah, blah, blah. Yeah, this value is less than, I keep the T, but this is epsilon max. This is the definition of epsilon approximation. We have epsilon, but we still have the annoying max here, right? But now the max is the same queries, because you didn't change the query space, but now it's about F prime PQ. And now you can understand why I define F prime the way I define. So F prime has the property that the sum is preserved, but now suddenly the maximum is only 1. So since actually we have, I'm sorry, this was epsilon over T corset. So this is just epsilon over, this is just less than epsilon, because again, by definition of prime, this is 1. So again, the reason why I define S like this is because when we look about the definition of F prime here, FPQ SP, it must be less than 1, because SP is the maximum possible value over all Q. So I don't know Q in advance. Since SP is the maximum over all Q, F prime is always less than 1. So the error max that I have there now disappear, and we have epsilon error. So this was essentially a reduction within the original data. I'll move from cos to this to F. Then I move from F to F prime. And then I just need to compute epsilon approximation for F prime. So there are two problems. How can I compute epsilon approximation? Can we compute it efficiently and small? This is very easy. This is related to visit dimension and random sampling usually. And we have so many results in the 78. We have visit dimension for decision trees, neural networks, whatever classifier you want. Just Google it and you find the visit dimension. So this is the easy part. The main part, the hard part, is to bound this SP. Sometimes just take a few minutes, someone comes with a problem, and after a few minutes we have SP, and it's not clear that we have a paper because it's so easy. So we have a corset. So now if you have a bound and SP and you know how to compute the visit dimension, you have a corset if the sum of the SP is not too large. Sometimes it takes a few years. For example, K-means with outlier, we spent 2 years in Caltech just to bound the SP, and we're saying that now we do some courses for Fourier transform. And again, it's sometimes extremely hard, but you don't have epsilon here. It's much elegant and smaller optimization problem that you can deal with, and then just plug it to this system. So there are still two things we need to do. So I want to just cite the theorem of Wapnick, how you actually compute epsilon approximation, and then give you examples, probably we'll continue tomorrow, how to actually bound sensitivity for problems that I showed, like K-means or SVD or matrix approximation. So usually, again, there were a lot of very long papers that describe how to do this. Now, after this, you just shoot 2 lines of proof how to bound the sensitivity, plug it to here, and you have a new corset, and instead of you reading a lot of very long papers of me and my friends using this kind of framework. So I have 10 minutes, so I'll give you a hint how we defined epsilon approximation. Is this the right things to do? I don't care. So let's just not erase this one and see how we can how we can compute epsilon approximation. So till now, I'm supposed to convince you that for a corset, all you need to do is find SP and compute epsilon approximation for the new set of function f prime. And the epsilon approximation might be easy if you're happy with random sampling. And this is the result of Vapnik. I want to know that this is an upper bound, but not a lower bound. So there are problems that the visible dimension is infinity. So you cannot use this technique. And still people show that you can get epsilon approximation. So, or for example, if you want a deterministic algorithm, this might not be the best tool for you. So it's just an upper bound, not a lower bound. You might find other technique, but the reduction is only for epsilon approximation. So I need to define the dimension of Q. That's what I mumbled in one of the slides. This is time to define what is mean the dimension of our query space. And for every positive R, we define the range of this R. So the range QR is how many points. So take a query Q, for example, point, and take all the points of distance at most R for this query. So for example, if the query is a point, you have radius R, so you cover some of the point or not from the input. So the range of QR is just a set of points that you cover. So again, in general, we don't talk about points and balls. We just have some distance function f, and you want to check how many points this cost, the weighted f, is less than r. So this defines the range QR. And the dimension now of Q, or more precisely of the query space, we have P, W, Q, and F, is the smallest, usually integer d, such that the following whole, for every subset in P, the number of possible range where Q is in Q and R is positive or non-negative less than S to the D. So what is the intuition behind this strange definition? So suppose that we take n points, how many subsets we have from n points? Order of. You must help me with this, even if you're unconscious. This is easy. How many? You have n points. How many subsets? You have n numbers. How many subsets you have in a group of n items? 2 to the n, more or less. So we have 2 to the n subset. But what if I ask you how many subsets you have such that you can cover this subset by a ball or a circle? So for example, these points, this set can be covered by a circle, but you don't have a circle that covers only this point and this point. So not every subset can be covered by one ball. So how many subsets you can define so that each subset is exactly separate from the other by some ball? And you can prove very easily, and again, this is the result of the visit dimension, pack learning, they prove all these things. For example, in this case, you have something like, I'm afraid to so if you have in d-dimensional space, or for example, if you're in two-dimensional space, you just enter to the some constant 2 or 3 at most. Why? Intuitively, for every set that you can cover by a ball, you can always move the ball so that, and scale it so that the ball will intersect 3 points. You can see that you move the ball until it intersects 1 point, then rotate it and it intersects the other point, then scale it down until it intersects a third point. So every set that is covered by a ball, you can always find an unique ball that covers this set and intersects 3 points. But if every set has such 3 representative points and we have about n points, so we have about n 3 such sets, which is order of n to the 3. In d-dimensional space, we won't have 3 points. We have about d or d plus 1 points. So the visit dimension is O of d. So this intuition is what's hidden in this equation. For every subset, the number of cover that you have is the number of points in the group to the d and not, for example, to the n. More practically, intuitively, d is just how many points or parameters you need to define your classifier. For example, to define a ball in two-dimensional space, you need the center, which is 2 x, y, 2 parameters, and the radius, which is r. So you get d equals 3. In d-dimensional space, the center is d parameters, so you need d plus 1 parameters. Now, this is not true. There are counterexamples when this trick doesn't work. Intuitively, practically, usually this is the case, the number of parameters you need to define the query. But again, if you want to prove things, you must use this strange definition. So now why do we care about this dimension? The reason that we care is that after you decide what is the dimension of your problem or you prove it, now all you need is to take random sample, uniform random sample, and the size of this sample is just depend on the error that you want, epsilon, and this dimension. So this is the main motivation for defining VC dimension, or dimension, which is kind of generalization of the VC dimension. So this is the famous theorem. This is the main theorem of pack learning, which was recently improved. I give all the credits in the last talk, but this is the main theorem. Again, I write it in our notation, but the idea is the same as the original one. So we have a query space of dimension d. So now we know what is the dimension. Now just take a uniform random sample. This is kind of the classic Corset. Let's see be a uniform random sample where P in P is sampled with probability proportional to its weight, proportional to the weight. So if all the points have the same weight, then it's just 1 over n, it's uniform sampling. If some point is more important, just use this importance. And we define a new weight. Every point in the corset will have the same weight, 1 over the size of the corset. Then, if you will sample at least, so the question how many points we want to get an epsilon approximation, and the claim is that if you sample d which is the dimension, plus log 1 over delta, where delta will be the probability of success. So what we get is the probability at least 1 minus delta C is an epsilon approximation of the query space. So epsilon approximation means for all the queries in the world, you're good. You have only epsilon error. So the probability here is in the same time for all the queries. This is something very important. It's not that if you give me a query, maybe I'll be good, maybe not. Because we have infinite number of queries and I will fail in some of them. No. For all the queries in the world, I will give you an epsilon error. And the probability this is true for all the queries in the world is at least 1 minus delta. But it's not for each query. This gives you the, so this is, we have here the error that you want, the epsilon, delta probability of success, note that it's log. So if you just take, log n points, the probability of failure is about 1 over n. So if you just pay very little, you get very, very high probability for success. D is the dimension. And now we can combine these. So let's just summarize what we have till now. So we begin with some distance cost function. So we begin with this. From this, we define cost. Then we define f, which was just this divided by sum of distances. From this, we define SP, which was the sensitivity. Using SP, we define a new function f prime and w prime. And then we show that we just need epsilon approximation. And for this, we show that we just need to take uniform sample, uniform up to the weights, but now based on this new function. So we change the weight of the function and just take uniform random sample from this set. In the end of the day, the code looks like this. Define a number of, find some good approximation for the optimal solution. Write S as the distance for each point to this solution, maybe scale, and take a weighted sampling based on this function. Weighted sampling is, for example, in MATLAB, we just weight sample or something like this. So there's one line MATLAB function that you just give the weights. MATLAB already will scale it to you, and then you can take a sample. So it's we'll end up with 3 lines of code. I'll try either tomorrow or on Friday talk about how we actually implement this thing and show some example codes. Amazingly easy. So I think it's a good point to stop today. I'll glad to answer questions either online or offline now. Any questions that you want to ask right now? Yes?
This is D plus log 1 over
Yeah, plus. It's a new result actually. So Vapnik has a wiki result a few years ago. I don't remember the names, but I'll give the credit. They get rid of some logs there. This was not the original Vapnik result, but it's a bit kind of a newer improvement in the recent years. Yes?
So are you sampling with probability WP or W dash?
So here there is no W dash, right? So this is self-contained. You just give me a query space with W, and it's according to W. Of course, in practice, after you go to this step, W you substitute W prime, and F will be F prime. Okay, I'm sorry if it's confusing. This is self-contained claim. More questions? Great. So if you want to talk to me about specific problems that you think that you might have cost for, I will be glad to help. I'm here till the weekend, and you can just send me an email, and we can schedule an appointment. I always talk with some of you, and it's I'm very, very excited about this. Thank you very much.